the Anthropic Principle. Why does the universe allow life? You are here, right now, in this moment, you exist. Your neurons fire, your heart beats, your mind processes these words. You breathe air composed of oxygen and nitrogen, sustained by a star burning hydrogen 93 million miles away, standing on a planet wrapped in a magnetic field that shields you from cosmic radiation, held to the surface by gravity strong enough to keep you grounded, but weak enough not to crush you. This simple fact, your existence is cosmically strange. The universe didn't have to be this way. It didn't have to permit complex structures like atoms, or stars, or planets, or the intricate chemistry that makes your body possible. The laws of physics could have been different. The fundamental constants could have taken other values. And if they had, even slightly, you wouldn't be here to contemplate them. Tonight, we're going to explore one of the deepest questions in all of cosmology, one that sits at the intersection of physics, philosophy, and meaning itself. We're going to ask, why does the universe allow life? Is it finely tuned for our existence? Or are we simply here to notice it? Are the cosmic conditions that make life possible the result of chance, necessity, design, or something else entirely? This is the question at the heart of the Anthropic Principle, and as we'll discover, the answers, or the lack of them, reveal as much about the nature of science itself as they do about the cosmos. So settle in. Let your mind drift through possibility and paradox, through precision and probability. We're about to take a journey from the largest scales of existence to the most intimate questions of meaning. And along the way, we'll encounter some of the strangest ideas in modern physics, some of the most heated debates in philosophy, and some of the most profound mysteries that consciousness has ever confronted. Let's begin where all science begins, with an observation. For most of human history, the universe simply was. The stars wheeled overhead, the sun rose and set, the seasons turned in their eternal cycle, and no one thought to ask why the fundamental rules of reality took the particular form they did. The laws of nature were as given and unquestionable as the air itself. But in the 20th century, something shifted. As physicists probed deeper into the structure of matter and the evolution of the cosmos, they began to notice something peculiar. The universe, it seemed, was balanced on a knife's edge. The fundamental forces that govern reality, gravity, electromagnetism, the strong and weak nuclear forces, all had to have very specific strengths for the universe to produce anything interesting at all. Change any of these forces even slightly, and the cosmos becomes a sterile wasteland. Too much of this, too little of that, and stars never form, or they burn out in an instant, or atoms can't exist, or chemistry is impossible. The parameter space that allows for complexity, for structure, for life, turns out to be extraordinarily narrow. This wasn't just speculation. This was mathematics, physics, the hard currency of science, and the numbers were startling. One of the first to notice this was the chemist Lawrence Joseph Henderson, who in 1913 wrote a book called The Fitness of the Environment. Henderson was struck by how perfectly suited water and carbon were for life, how the properties of these substances seemed almost designed for biological complexity. Of course, Henderson was writing before modern cosmology, before we understood stellar nucleosynthesis or the quantum mechanical basis of chemistry. But his intuition that the universe seemed remarkably hospitable to life would echo through the decades to come. In 1961, the physicist Robert Dicke took the observation further. Various fundamental constants in physics, when you formed certain dimensionless ratios from them, all seemed to come out to roughly the same enormous number, around 10 to the 40th power. The ratio of the electromagnetic force to the gravitational force between two protons. The ratio of the age of the universe to the time it takes light to cross an atom. These wildly different quantities, with no obvious connection, somehow yielded similar values. Why? What could possibly link the scale of the atom to the scale of the cosmos? Dicke realized something important. The age of the universe couldn't be arbitrary if we were asking the question. It had to be old enough for stars to have formed, burned through their hydrogen, exploded as supernovae, seeded space with heavy elements, allowed second-generation stars and planets to form, and given time for life to evolve. The universe had to be billions of years old for observers like us to exist. And because the universe is expanding, its age is directly related to its size. So the cosmos had to be vast billions of light years across, simply because it had to be old enough for us to be here asking about it. The coincidence wasn't a coincidence at all. It was a selection effect. We necessarily find ourselves at a time and place in cosmic history where these ratios happen to have these values, because that's the only kind of place where observers can exist. This was a profound realization, though Dicke didn't give it a catchy name. He simply used it to explain away what had seemed like a mysterious pattern in the constants of nature. But others would take the idea much further. By the 1970 seconds, physicists and cosmologists had accumulated a growing list of these cosmic coincidences. The strength of gravity compared to other forces, the mass of the electron compared to the proton, the rate of expansion of the universe, the properties of the carbon nucleus that allow it to form in stars. Each one fell within a narrow range that permitted the existence of complex chemistry and therefore life. The universe began to look less like an arbitrary arrangement and more like a finely balanced mechanism, every parameter tuned to permit or even encourage the emergence of observers. This wasn't the result of measurement error or wishful thinking. These were hard numbers derived from well-tested physical theories. The observation was clear. We live in a universe that seems remarkably suited to our existence. The question was, what do we make of that fact? In 1973, astronomers and cosmologists gathered in Krakow, Poland, to celebrate the 500th anniversary of the birth of Nicolaus Copernicus. It was a fitting occasion. Copernicus, after all, had fundamentally reshaped humanity's understanding of its place in the cosmos. His revolutionary model placed the sun, not the Earth, at the center of the solar system. In doing so, he launched what we might call the Copernican Revolution, the gradual realization that humanity occupies no special position in the universe. Over the centuries, that lesson has been reinforced again and again. Earth is not the center of the solar system. The solar system is not the center of the galaxy. Our galaxy is not the center of the universe. There is no center. We live on an ordinary planet, orbiting an ordinary star in an ordinary galaxy drifting through the vast expanse of space. We are not special. This principle that our cosmic address is unremarkable has guided astronomical thinking for half a millennium. But at that conference in Krakow, a young physicist named Brandon Carter stood up to deliver a paper that would challenge this Copernican orthodoxy, or at least complicate it considerably. His presentation was titled Large Number Coincidences and the Anthropic Principle in Cosmology. It was the first time anyone had used the term Anthropic Principle in print. Carter's insight was deceptively simple, but its implications would reverberate through cosmology and philosophy for decades. He argued that while our position in the universe might not be central, it is nevertheless inevitably privileged in certain ways. Why? Because we are observers, and any universe we observe must, by logical necessity, be capable of producing observers. This might sound tautological. Of course, we find ourselves in a universe that permits our existence, because otherwise we wouldn't be here to find anything. But Carter argued that this selection effect had real scientific utility. It could help explain why certain physical constants take the values they do, not because those values are fundamental or unique, but because those are the values compatible with observers existing to measure them. Carter proposed two versions of what he called the Anthropic Principle, carefully distinguishing between them. The first he called the weak Anthropic Principle. It stated simply that the observed values of all physical and cosmological quantities are not equally probable, but are restricted by the requirement that observers exist to make the observations. In other words, we shouldn't be surprised that we find ourselves in a region of space and time where the conditions allow for life, because we couldn't find ourselves anywhere else. The second version, which Carter called the strong Anthropic Principle, went further. It suggested that the universe must have those properties which allow life to develop within it at some stage in its history. This formulation implied something more profound, more controversial, a sense of cosmic necessity, perhaps even purpose. Carter himself would later express regret about his choice of the word anthropic. It comes from the Greek anthropos, meaning human, and it carries the misleading suggestion that the principle is specifically about humanity. It was about observers in general, about any form of intelligent life capable of examining the universe. He might have better called it the observation principle or the observer selection principle. But anthropic principle was the phrase that stuck, and it has caused no end of confusion ever since. The term principle itself has also come under fire. Some critics argue that it's too grandiose a word for what is essentially a straightforward application of selection effects. A principle, in physics, usually means a fundamental rule or law that governs how nature operates. The anthropic principle doesn't govern nature, it governs how we reason about nature when we're necessarily part of the picture. But whatever we call it, Carter's idea marked a turning point. It forced scientists to confront a peculiar feature of cosmology that distinguishes it from other sciences. When we study chemistry or biology or geology, we can, in principle, maintain the fiction of the detached observer, the scientist examining a system from the outside. But in cosmology, we are studying the whole universe, and we are inside it. And that means we can't ignore the fact of our own existence when we try to explain why the universe has the properties it does. The weak anthropic principle, at least, seemed difficult to dispute. It was a reminder to be careful about selection bias, to remember that the universe we observe is necessarily filtered through the requirement that observers can exist. This might seem obvious, but as we'll see, even this modest claim has profound implications for how we interpret the fine-tuning we observe. The strong anthropic principle, on the other hand, opened a Pandora's box of philosophical and theological questions. Is it logical necessity? Physical necessity? Some kind of cosmic teleology? A purpose woven into the fabric of reality itself? Carter didn't provide definitive answers to these questions. Perhaps he couldn't. But by clearly articulating the problem and giving it a name, he ensured that physicists and philosophers would grapple with it for generations to come. Over the following decade, others would expand on Carter's ideas. In 1986, physicists John Barrow and Frank Tipler published The Anthropic Cosmological Principle, a massive and controversial book that cataloged no fewer than 30 different versions of the anthropic principle, ranging from the sensible to the wildly speculative. They added their own formulations, including what they called the final anthropic principle, which claimed that once life arises in the universe, it will never disappear, that intelligence is somehow a permanent feature of reality. These elaborations and the debates they sparked showed both the power and the peril of Carter's original idea. The anthropic principle could illuminate real puzzles in cosmology, helping us avoid errors in reasoning about a universe we inhabit. But it could also slide into speculation, into claims that sounded profound but might be empty of content, into a kind of cosmic narcissism that placed observers at the center of the explanatory story. To understand these tensions, we need to look more carefully at what the different versions of the anthropic principle actually say, and what work they can legitimately do in science. Let's start with the weak anthropic principle, because it's the version that most scientists find relatively unproblematic, even if they sometimes disagree about how useful it is. The weak anthropic principle, in its essence, says this: the fact that we observe certain values for physical constants and cosmological parameters doesn't mean those values are typical or fundamental. It just means they're compatible with our existence. We're seeing a biased sample of reality, biased by the precondition that observers must exist to do the observing. Think of it this way. Imagine you're a fish, and you've spent your entire life in water. You might be tempted to conclude that the whole universe is aquatic, that water is the natural and universal condition of existence. But of course, you'd be wrong. You're just experiencing a selection effect. Fish only exist where there's water, so fish only observe watery environments, even though most of the universe is decidedly non-aquatic. The weak anthropic principle is a reminder not to make the fish's mistake when we do cosmology. Yes, we observe a universe with stars and galaxies and chemistry and life, but we have to ask, is this typical? Or are we necessarily observing an atypical corner of reality simply because typical corners don't produce observers? Robert Dicke, as we mentioned earlier, used this kind of reasoning to explain those large number coincidences. The age of the universe, he argued, couldn't be just anything if we're here to measure it. It had to be old enough for stellar nucleosynthesis to produce carbon, for planets to form, for life to evolve. So we shouldn't be surprised to find ourselves at a cosmic epoch where these particular numerical relationships hold, even if they seem like bizarre coincidences at first glance. This is the weak anthropic principle in action. It's not explaining why the universe has the properties it does in any deep sense. It's not providing a mechanism or a fundamental theory. It's just reminding us to account for selection bias when we interpret our observations. And this, critics argue, is precisely the problem. The weak anthropic principle seems to be a tautology, a statement that's true by definition and therefore explains nothing. Of course, we find ourselves in conditions compatible with our existence. How could it be otherwise? Saying we observe what permits us to observe is like saying bachelors are unmarried, true, but not particularly enlightening. Defenders of the weak anthropic principle respond that even if it's tautological in some sense, it's not trivial. And the history of science is full of cases where people made mistakes precisely because they didn't account for selection effects. Consider the long-standing puzzle in cosmology about why the early universe had such incredibly low entropy. Entropy is a measure of disorder, and the second law of thermodynamics tells us that entropy always increases over time. So, if we run the clock backwards, the universe must have started in an extraordinarily improbable, low entropy state. Why? That seems to demand an explanation. But here's where the weak anthropic principle might offer some insight. Perhaps the universe as a whole, or the multiverse, if such a thing exists, has regions of high entropy and regions of low entropy. We necessarily find ourselves in a low entropy region because high entropy regions are thermodynamic, equilibrium, dead, uniform, structureless. No stars, no planets, no life, no observers. We can only exist in the rare regions where entropy is low enough to permit structure and complexity. Does this fully explain the low entropy of the early universe? Not entirely. There are still deep questions about the global structure of reality and the arrow of time, but it does shift our perspective. It makes us realize that we shouldn't necessarily expect to find ourselves in a typical region of the cosmos, because typical regions might be uninhabitable. This is the proper use of the weak anthropic principle. It's not a substitute for deeper physical explanations, but it's a check against naive reasoning. Now let's turn to the strong anthropic principle, which is far more controversial. The strong anthropic principle says that the universe must have properties that allow life to develop within it at some stage in its history. Notice the crucial word, must. Not happens to, but must. What could that possibly mean? One interpretation is teleological. The universe, on this reading, has a purpose or a goal, and that purpose is to produce observers. Life isn't an accident or a side effect, it's the reason the universe exists at all. Physical constants are finely tuned because they need to be, because the whole cosmic drama is oriented toward the emergence of consciousness. This interpretation tends to make scientists deeply uncomfortable. Modern science, at least since the Enlightenment, has systematically removed purpose and intention from our explanations of nature. The planets don't orbit the sun because they're trying to achieve anything. Water doesn't flow downhill because it wants to. Lightning doesn't strike because the gods are angry. Natural phenomena happen because of physical laws and initial conditions, not because of cosmic intentions. The strong anthropic principle, if interpreted teleologically, seems to reverse this hard-won progress. It reintroduces purpose into physics, and with it, the specter of religious or metaphysical claims that science can't test or verify. No wonder most working physicists reject it. But there's another way to interpret the strong anthropic principle, one that's less metaphysically loaded. Perhaps must doesn't refer to purpose or intention, but to logical or physical necessity given certain other constraints. If, for instance, there's a vast ensemble of universes with different properties, what we now call the multiverse, then it might be necessarily true that some of those universes allow life. And if observers can only exist in life-permitting universes, then it's necessarily true that observers find themselves in such universes. On this interpretation, the strong anthropic principle becomes a claim about the structure of reality itself. It says, given the way things actually are, whatever that turns out to be, observers must arise somewhere. This is less a claim about purpose and more a claim about possibility and probability in an ensemble of universes. But even this interpretation faces serious challenges. How do we know there's a multiverse? How would we test such a claim? And even if there is a multiverse, why should we believe it exhausts all possible universes? These are questions we'll return to when we discuss multiverse theories. For now, it's worth noting that even Brandon Carter, who coined these terms, was careful to distinguish his formulations from more extravagant claims. His strong anthropic principle was meant to be a scientific tool, a way of thinking about constraints on physical theories. He wasn't endorsing cosmic purpose or intelligent design, but once the terminology was out there, others couldn't resist pushing it further. John Barrow and Frank Tipler, in their 1986 book, proposed additional versions. There's the participatory anthropic principle, inspired by John Archibald Wheeler's musings about quantum mechanics, which suggests that observers are somehow necessary to bring the universe into being. And then there's the final anthropic principle, which claims that once intelligent information processing arises in the universe, it will persist forever. This isn't just saying life is possible, it's saying life is eternal, an indelible feature of the cosmos. These more exotic versions of the anthropic principle veer away from science and into philosophy or even theology. They're speculation piled on speculation. Most physicists ignore them, and for good reason. They make grand claims that we have no way to test, and they don't seem to do any useful work in helping us understand the actual universe we inhabit. But the core versions, Carter's weak and strong formulations, remain subjects of genuine scientific and philosophical debate. The weak principle seems like a legitimate corrective to certain kinds of reasoning errors, even if it doesn't by itself explain anything. The strong principle remains controversial, its meaning and implications still contested. What both versions force us to confront is the central puzzle. The universe does appear to be finely tuned for life. Whether we call that an anthropic selection effect, a cosmic coincidence, or something deeper, the fact remains. And to appreciate just how fine that tuning is, we need to look at the specific numbers, the precise values of the constants that make our existence possible. Let's turn now to the razor's edge on which reality balances. When physicists talk about fine-tuning, they're not being poetic or vague. They're referring to specific, measurable quantities whose values fall within extremely narrow ranges that permit the existence of complex structures like atoms, stars, and living organisms. Let's walk through some of the most striking examples, and let's be precise about the numbers, because the scale of the fine-tuning, the sheer improbability of getting these values right by chance, is part of what makes the anthropic principle seem necessary, or at least relevant. We'll start with perhaps the most dramatic case, the cosmological constant. The cosmological constant, usually denoted by the Greek letter lambda, appears in Einstein's equations of general relativity. It represents a kind of energy density inherent in empty space itself, what we now call dark energy. This energy has a repulsive gravitational effect. It causes space to expand, and in our universe, that expansion is accelerating. The observed value of the cosmological constant is extraordinarily small, but positive vanishingly tiny, yet not quite zero. That small positive value is crucial for our existence. Here's the problem. When quantum field theorists try to calculate what the cosmological constant should be based on quantum mechanical principles, they get a number that's about 10 to the 120th power, larger than what we observe. That's not a typo. The theoretical prediction is off by a factor with 120 zeros after it. This is sometimes called the worst prediction in the history of physics, and it's earned that title. Now, there are various ways to think about this discrepancy. Maybe the calculation is wrong. Maybe there's some mechanism we don't understand that cancels out most of the quantum contribution. But whatever the explanation, the fact remains. The actual value of the cosmological constant is extraordinarily small compared to what we might expect. And that small value is crucial for life. If the cosmological constant were much larger, even by a tiny fraction, in absolute terms, the universe would have expanded so rapidly that galaxies never could have formed. Matter would have been flung apart before gravity had a chance to pull it together into stars and planets. The cosmos would be a thin, cold, uniform gas, forever racing away from itself. If, on the other hand, the cosmological constant were negative, the universe would have collapsed in on itself long before stars could ignite, let alone create the heavy elements necessary for life. The life-permitting range has been estimated to be about 1 part in 10 to the 120th. To visualize just how fine that tuning is, imagine a measuring line stretching across the entire observable universe 93 billion light-years from end to end. If the full range of possible values for the cosmological constant spans that distance, the life-permitting range is about the width of a single atom. Actually, even smaller. Much smaller. The life-permitting range on that cosmic measuring stick would be invisible to any microscope we could ever build. That's the cosmological constant. But it's not the only finely tuned parameter. Consider gravity. The strength of gravity is determined by a constant called g, Newton's gravitational constant. Gravity is extraordinarily weak compared to the other fundamental forces. The electromagnetic force between two protons is about 10 to the 36th power stronger than the gravitational force between them. Why does this matter? Because if gravity were much stronger relative to the electromagnetic force, stars would burn out far too quickly to support the long, stable lifetimes needed for planets to form and life to evolve. A star's lifetime depends on a delicate balance between the inward pull of gravity and the outward pressure from nuclear fusion. Make gravity stronger, and you need more fusion to resist collapse, which means burning through fuel faster. Stars might last mere millions of years instead of billions. If gravity were weaker, stars might never form at all. The gas clouds that collapsed to create the first stars would lack sufficient gravitational pull to ignite fusion in their cores. The life-permitting range for the strength of gravity, when compared to electromagnetism, is estimated to be about 1 part in 10 to the 34th. On that universe-sized measuring stick, the acceptable range would be about 9 nanometers wide, roughly the width of an average protein molecule. We are threading a needle on cosmic scales. Now, let's look at the strong nuclear force, the force that holds the nuclei of atoms together. Protons in a nucleus are all positively charged, and like charges repel. The electromagnetic force should blow any nucleus apart, but the strong force overcomes this repulsion, at least at very short distances, binding protons and neutrons together. The strength of the strong force is characterized by a coupling constant. Change that constant by more than about 2%, and the universe becomes drastically different. If the strong force were just 2% stronger, something strange would happen. The deuteron, a nucleus made of 1 proton and 1 neutron, is currently just barely stable. Make the strong force slightly stronger, and a new kind of nucleus becomes stable. The diproton, 2 protons bound together with no neutrons. Why does this matter? Because in the early universe, if diprotons were stable, hydrogen fusion in stars would have proceeded along a different pathway. Instead of the slow process we see in our sun, where hydrogen gradually fuses into helium, all the hydrogen in the universe would have been converted to helium and heavier elements very quickly, perhaps even during the Big Bang itself. A universe with a slightly stronger strong force would have no hydrogen left over. No hydrogen means no water. No water means no life, at least not life as we understand it. And no hydrogen also means stars would have no long-term fuel. They'd burn through heavier elements much more quickly, living fast and dying young. On the other hand, if the strong force were about 2% weaker, the consequences would be equally catastrophic, just in the opposite direction. Deuterium, the nucleus that's a stepping stone in stellar fusion, would no longer be stable. And without deuterium, the chain of nuclear reactions that builds up heavier elements in stars would be broken. A universe with a slightly weaker, strong force might have nothing but hydrogen and helium. No carbon, no oxygen, no nitrogen, no phosphorus, none of the heavy elements that make planets and life possible. Chemistry as we know it simply wouldn't exist. The fact that the strong force falls precisely in the narrow window that allows both hydrogen and heavy elements to exist is, from a naive probability perspective, extraordinarily unlikely. The weak nuclear force, which governs certain kinds of radioactive decay, also has to fall within a specific range. This force is responsible for processes that are crucial in stellar interiors, including some of the reactions that power the sun. Too strong or too weak, and stars wouldn't be able to forge the elements or maintain stable lifetimes. Then there's electromagnetism itself. The strength of electrical and magnetic forces is determined by another constant, the fine structure constant. This constant governs everything from the binding energies of electrons in atoms to the details of how light interacts with matter. If electromagnetism were significantly stronger, electrons would be bound so tightly to nuclei that chemical reactions would be dramatically different if they could occur at all. Molecular bonds, the basis of chemistry and biology, depend on electrons being shared or transferred between atoms. Change the strength of electromagnetism too much, and you change the entire landscape of possible chemical interactions. If electromagnetism were much weaker, atoms would be larger and more diffuse. Chemical bonds would be weaker, and again, the delicate chemistry of life would be impossible. The ratio of electromagnetism to gravity also affects stars in crucial ways. Stars exist in different types, red dwarfs, sun-like stars, blue giants, depending on their mass and the balance of forces within them. The distribution of stellar types in our universe allows for stable, long-lived stars like our Sun. Change the electromagnetic to gravitational force ratio significantly, and you might get a universe with only red dwarfs, too cool and dim to support life on nearby planets, or only blue giants, which burn out too quickly. What makes all of this even more remarkable is that it's not just individual constants that have to fall within narrow ranges. The ratios between different constants also matter. The forces don't operate in isolation, they interact, and the balance between them is crucial. For instance, the formation of galaxies depends on a delicate interplay between gravity, dark matter, and dark energy. If any one of these were significantly different, galaxies might never have formed, or they might have formed and then been torn apart by expansion before stars could ignite. The production of heavy elements in stars depends on the interplay of all four fundamental forces. Each step in the chain of nuclear reactions that builds carbon from helium or oxygen from carbon depends on the precise strengths of the forces involved. Change any of them, and the cosmic factory that manufactures the ingredients of life shuts down. This is what physicists mean when they talk about fine-tuning. It's not a vague sense that things seem convenient. It's a specific, quantifiable observation that multiple fundamental parameters of the universe fall within extremely narrow ranges that permit complexity, and that changing any of them even slightly would result in a sterile cosmos. Some have estimated that if you consider all the various parameters that need to be within certain ranges, the probability of getting a life-permitting universe by random chance is staggeringly small. Numbers, like 1 in 10 to the 100th power, are thrown around, though it's worth noting that such calculations depend on assumptions about probability distributions that we can't really verify. But even if the exact numbers are debatable, the basic conclusion isn't. The universe we inhabit sits in a tiny corner of parameter space where the conditions are just right for stars, chemistry, and life. Tweak almost anything, and that window closes. This is the fact that the Anthropic Principle tries to make sense of. It's not a matter of opinion or interpretation. It's data, emerging from our best physical theories. The question is, what do we do with this data? Does it require explanation, or is it simply a brute fact? If it does require explanation, what form should that explanation take? Before we explore the full range of responses to these questions, the multiverse, design arguments, alternative theories, there's one particular historical case of fine-tuning that deserves special attention. It deserves our focus, both because of its scientific importance and because of the fascinating human story behind it, a story that has become entangled with the Anthropic Principle itself in ways that illuminate how scientific myths are born. It's the story of a prediction made by one of the 20th century's great astrophysicists, a prediction that seemed audacious at the time, but turned out to be precisely correct. It's the story of Fred Hoyle and the carbon resonance. Carbon is essential for life. At least, it's essential for the only kind of life we know life on Earth. Life built from organic chemistry. Life where carbon atoms form the backbones of complex molecules that can encode information, catalyze reactions, and build cellular structures. Silicon is sometimes suggested as an alternative, but carbon has properties that make it uniquely suited for biochemistry. It forms strong bonds with itself and with other elements. It can create chains, rings, branching structures of arbitrary complexity. The chemistry of life, as far as we understand it, requires carbon. But where does carbon come from? Not from the Big Bang. In the early universe, only the lightest elements were created: hydrogen, helium, trace amounts of lithium, and beryllium. Everything heavier, carbon, oxygen, iron, all the elements that make up planets and people had to be forged later in the nuclear furnaces at the hearts of stars. The process by which this happens is called stellar nucleosynthesis, and by the early 1950 seconds, physicists were beginning to work out the details. They understood that stars fuse hydrogen into helium, releasing energy in the process. And they knew that when stars exhausted their hydrogen, they could begin fusing helium into heavier elements. But there was a problem with making carbon. The most direct way to produce carbon would be to fuse 3 helium nuclei, 3 alpha particles, into a single carbon nucleus. Helium-4 plus helium-4 plus helium-4 equals carbon-1,2. Simple arithmetic. But the physics is not so simple. The first step would be to fuse 2 helium nuclei into beryllium-8. And here's where things go wrong. Beryllium-8 is extremely unstable. It has a half-life of about 8.19 times 10 to the minus 17 seconds. That's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 For the triple alpha process to work, a third helium nucleus would have to slam into that fleeting beryllium-8 nucleus during its impossibly brief existence and fuse with it to create carbon-1,2. The odds seemed prohibitively small. In 1952, the physicist Edwin Salpeter published a paper showing that, under the extreme conditions in the cores of red giant stars, temperatures around 100 million degrees Kelvin, densities around 100,000 grams per cubic centimeter, the triple alpha reaction could, in principle, proceed. The beryllium-8, even though unstable, exists in a kind of equilibrium with the helium. There's always a tiny bit of it present, and occasionally, a helium nucleus collides with it before it decays. But Salpeter's calculations suggested the reaction rate would be low, perhaps too low to account for the amount of carbon we actually observe in the universe. The numbers didn't quite add up. Enter Fred Hoyle, one of the great scientific characters of the 20th century. Hoyle was a brilliant astrophysicist, a pioneer of stellar nucleosynthesis theory, and also a staunch advocate of the steady-state model of the universe, which competed with the Big Bang theory. He was also the man who, somewhat ironically, coined the term Big Bang during a BBC radio broadcast, intending it as a dismissive nickname for a theory he opposed. The name stuck, though Hoyle's preferred steady-state model did not. In 1953, Hoyle was thinking about the carbon problem. He knew carbon was abundant in the universe. Stars create it, supernova explosions distribute it, planets contain it, and life depends on it. Therefore, he reasoned, there must be a way for stars to make it efficiently. Working backward from the observed abundance of carbon, Hoyle realized something. For the triple alpha process to produce carbon at the rate required, there had to be a resonance in the carbon-1,2 nucleus at just the right energy level. Let me explain what that means. Atomic nuclei can exist in different energy states, like different notes on a musical instrument. The ground state is the lowest energy, the most stable, but nuclei can also be excited to higher energy levels. These excited states are called resonances, and they play a crucial role in nuclear reactions. If the energy of an incoming particle matches the energy difference between the ground state and an excited state, the reaction proceeds much more efficiently. It's like pushing a child on a swing. If you push at just the right frequency, the resonance of the swing amplifies your effort. Hoyle calculated that for the triple alpha process to work at the necessary rate, carbon-1,2 had to have an excited state at about 7.7 million electron volts above the ground state. Moreover, this resonance had to have specific quantum properties, a spin of 0 and positive parity, what physicists call a 0+ state. The problem was, no one had ever observed such a state. The existing experimental data on carbon-1,2 didn't include any resonance at 7.7 MeV. Undeterred, Hoyle traveled to Caltech, where William Fowler led a nuclear physics research group. Hoyle walked into the lab and, with characteristic confidence, told Fowler and his team that there had to be a resonance in carbon-12 at 7.7 MeV. It had to exist, because otherwise, stars couldn't make enough carbon. The nuclear physicists were skeptical. You don't normally predict new nuclear physics states by working backward from the existence of carbon in the universe. You discover them through careful experiments and theoretical calculations. Hoyle's approach seemed audacious, even presumptuous. But a young physicist named Ward Whaling, fresh out of graduate school and looking for a research project, decided to test Hoyle's prediction. He and his colleagues bombarded nitrogen nuclei with deuterium, producing excited states of carbon-1, 2, and carefully measured the resulting energy levels. And they found it. A resonance at 7.65 MeV, almost exactly where Hoyle had predicted. And it had the right quantum properties. Spin zero, positive parity, a zero-plus state. This discovery, which we now call the Hoyle state, was a triumph. It vindicated Hoyle's reasoning about stellar nucleosynthesis and provided the missing piece of the puzzle for how carbon is created in stars. The triple alpha process proceeds through this resonance, making carbon formation efficient enough to explain the universe's carbon abundance. Later, Hoyle, Fowler, and two others, Geoffrey and Margaret Burbidge, published a landmark 1957 paper titled Synthesis of the Elements in Stars. Known as the B² FH paper, from the initials of the author's names, it laid out the detailed nuclear pathways by which stars create elements from hydrogen all the way up to iron. It was one of the great achievements of 20th century astrophysics. In 1983, William Fowler received the Nobel Prize in Physics for his work on nucleosynthesis. Many people, including Fowler himself, felt that Hoyle should have shared the prize. His exclusion remains one of the Nobel Committee's more controversial decisions. But there's another aspect to this story, one that relates directly to the Anthropic Principle. In popular accounts, Hoyle's prediction of the carbon resonance is often described as the first successful application of anthropic reasoning. The logic goes like this. Hoyle observed that we exist and that we are made of carbon. He reasoned backward from our existence to the conclusion that stars must be able to make carbon efficiently, and from that, he predicted the resonance. It's a compelling narrative. It would make the Hoyle state the poster child for the Anthropic Principle, a case where anthropic reasoning led to a genuine, testable prediction that turned out to be correct. There's just one problem with this narrative. It's not quite true. Historical research into Hoyle's original 1,953 papers and correspondence shows that he did not, in fact, invoke the existence of life or observers when making his prediction. He reasoned from the observed abundance of carbon in stars and the requirements of stellar nucleosynthesis. It was a purely astrophysical argument, not an anthropic one. The anthropic interpretation came later, in the 1,970 seconds and 1,980 seconds, after Brandon Carter coined the term Anthropic Principle, and after people began looking for examples of where such reasoning might be useful. Hoyle himself, in his later years, did sometimes describe his prediction in anthropic terms, and he even went so far as to argue that the fine-tuning of the carbon resonance was evidence for a super intellect having designed the universe. But this was a retrospective interpretation, not his original reasoning, so the anthropic myth of the Hoyle state, while widely repeated, is just that, a myth. It's a story that many people think ought to be true. That would be a perfect illustration of the Anthropic Principle in action, but which doesn't match the historical record. That said, the Hoyle state remains a genuine example of fine-tuning. The resonance at 7.65 MeV is remarkably well placed for carbon production. The acceptable range is narrow. If the resonance were at 7.3 MeV or below, it wouldn't help the triple alpha process, because there wouldn't be enough energy available from the colliding particles. If it were at 7.9 MeV or above, it would be too high for the reaction to proceed efficiently. The life-permitting window is estimated to be somewhere between 7.596 and 7.716 MeV for the observed abundance of carbon. Moreover, there's a second piece of fine-tuning related to oxygen. After carbon forms, it can capture another helium nucleus to form oxygen-1,6. If this reaction proceeded too efficiently, all the carbon would be converted to oxygen, and we'd end up with a universe rich in oxygen but poor in carbon. Fortunately, there's a resonance in oxygen-1,6 that's slightly too low to make this reaction highly efficient. The balance is delicate. Enough carbon survives to be cosmically abundant, but enough oxygen forms to be crucial for chemistry and life. These are the kinds of coincidences that drive the fine-tuning debate. Are they truly remarkable, or are we just noticing the cases that happen to work in our favor while ignoring all the parameters that could vary without affecting life? The Hoyle state remains a powerful example because it's so concrete. It's not an abstract constant, it's a specific energy level in a specific nucleus, and we can calculate exactly what would happen if it were different. And the answer is no carbon, or very little carbon, in the universe. And without carbon, no life as we know it. Whether you interpret this as anthropic reasoning, divine design, or simply a fortunate accident depends on your philosophical priors. But the fact itself is undeniable. We live in a universe where the carbon nucleus happens to have exactly the right properties to allow its own synthesis in stars. And that's precisely the kind of observation that demands some kind of response, even if we're not sure what that response should be. For many physicists, the response has been to invoke the multiverse. If there are countless universes with different physical laws and constants, then perhaps it's not so surprising that we find ourselves in one of the rare universes where the constants permit life. After all, we couldn't find ourselves anywhere else. Let's turn now to that idea, the multiverse, and see how it attempts to resolve the fine-tuning puzzle. If the universe appears finely tuned for life, there are several possible explanations. One is designed some intelligence, deliberately chose the parameters to allow for observers. Another is necessity. Perhaps a deeper theory we haven't discovered yet will show that the constants couldn't have been anything other than what they are. A third is sheer luck, we won the cosmic lottery, and here we are. But there's a fourth possibility, one that has gained considerable traction among physicists and cosmologists over the past few decades. It's the idea that our universe is not unique, that there are, in fact, a vast number of universes, perhaps infinitely many, each with different physical laws and constants. In this scenario, the fine-tuning we observe isn't surprising at all. It's a selection effect. We find ourselves in a life-permitting universe simply because we couldn't exist in any other kind. This is the multiverse hypothesis, and it comes in several varieties. The version most relevant to the Anthropic Principle arises from a theory called cosmic inflation, combined with insights from string theory. Let's build up this idea step by step. In 1981, the physicist Alan Guth proposed the theory of cosmic inflation to solve several puzzles about the early universe. The Big Bang model, while successful in many ways, had some problems. One was the horizon problem. Why is the universe so uniform on large scales? Different regions of space, separated by distances so vast that light hasn't had time to travel between them since the Big Bang. Nevertheless, have almost identical properties, the same temperature, the same density, the same laws of physics. How did they know to be so similar if they were never in causal contact? Guth's solution was elegant. In the first fraction of a second after the Big Bang, around 10 to the minus 36 seconds, the universe underwent a period of exponential expansion. Space itself inflated, growing faster than the speed of light. During this brief but dramatic epoch, a tiny region of space that was uniform and in thermal equilibrium was stretched to enormous size, much larger than our current observable universe. This explained the uniformity problem. Distant regions of space appear similar because they were once close together, in equilibrium, before inflation separated them. It's like taking a tiny dot and stretching it into a vast canvas. The canvas retains the properties of the dot, just expanded over a much larger area. Inflation also predicted specific patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang. In 2003, satellite observations confirmed these predictions with stunning precision. Cosmic inflation went from a speculative idea to a cornerstone of modern cosmology, but physicists soon realized something strange about inflation. If it could start, it might not stop, at least not everywhere at once. In 1983, physicists Paul Steinhardt, Andrei Linde, and Alexander Vilenkin independently came to a startling conclusion. In most models of inflation, once the inflationary expansion begins in a region of space, quantum fluctuations ensure that some subregions keep inflating even as others stop. Those inflating subregions spawn their own sub-subregions, some of which also keep inflating. The process continues indefinitely. The result is what Linde called eternal inflation. Even though inflation ends in particular regions, creating bubble universes like ours, the process as a whole never stops. It's a kind of cosmic reproduction, with inflating regions constantly spawning new bubble universes, each of which is, for all practical purposes, its own separate cosmos. From inside one of these bubbles, like the one we inhabit, the universe appears to have started with a Big Bang and then expanded at a more sedate rate. We see a finite, observable universe, bounded by the distance light has been able to travel since our local inflation ended. But beyond our cosmic horizon, the greater reality is an infinite sea of bubble universes, each potentially with its own beginning, its own history, its own fate. This was already a radical idea, but it became even more radical when combined with string theory. String theory is widely considered one of the most promising attempts to unify all the forces of nature, including gravity, into a single, consistent framework. Instead of thinking of particles as point-like objects, string theory proposes that they're tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, quarks, photons, and so on. The mathematics of string theory is extraordinarily complex, and it comes with some unusual requirements. For the theory to be mathematically consistent, space must have more dimensions than the 3 we experience. Most versions of string theory require 10 or 11 dimensions. Where are these extra dimensions? According to the theory, they're curled up, compactified into structures so small that we can't detect them. It's like the difference between a garden hose and a wire from a distance. From far away, a garden hose looks one-dimensional, like a line, but up close, you can see it has a circular cross-section. It's actually 3-dimensional, but 2 of those dimensions are curled into a tiny circle. In string theory, 6 or 7 dimensions are supposedly curled up at every point in space, but they're so small on the order of the Planck length, about 10 to the minus 35 meters, that we can't see them. We experience space as 3-dimensional plus time. But according to string theory, there's more to reality than meets the eye. Here's the catch. There are many ways to curl up those extra dimensions. Many, many ways. Calculations suggest that there are at least 10 to the 500th power, that's 1 followed by 500 zeros, possible ways to compactify the dimensions of string theory. This vast collection of possibilities is called the string landscape. Each point in the landscape corresponds to a different configuration of the extra dimensions, and each configuration leads to different effective laws of physics in the three large dimensions we inhabit. Different masses for particles, different strengths for the fundamental forces, even different numbers of particle types. In other words, the string landscape gives you a vast menu of possible universes, each with its own physics. Now, combine eternal inflation with the string landscape. In the string landscape, you get a vast number of possible physical configurations. Put them together, and you get a scenario where different bubble universes realize different points in the landscape. Some bubbles have one set of physical constants, others have different constants. Across the multiverse as a whole, an enormous range of possibilities is explored. And here's where the Anthropic Principle enters the picture. If there are bubbles with all these different physical properties, then in most of them, the constants won't be right for life. Stars won't form, or chemistry won't work, or the universe will collapse too quickly. But in a tiny fraction of bubbles, maybe 1 in 10 to the 100th power, or some such absurdly small number, the constants will happen to fall within the narrow range that permits complexity in life. We, necessarily, find ourselves in one of those rare bubbles, not because our universe is special or designed, but because we couldn't exist anywhere else. It's a selection effect on a cosmic scale. This is an elegant solution to the fine-tuning problem. It removes the need for a designer or for some mysterious cosmic necessity. The constants are what they are in our bubble because there are bubbles with all possible constants, and we can only observe the ones compatible with our existence. It also makes the weak anthropic principle straightforwardly true. Of course, we observe constants that permit observers. In a multiverse, there's no other possibility, but does this explanation actually work? Does it genuinely solve the problem, or does it just push the mystery back a level? There are several reasons to be cautious about embracing the multiverse as the final answer. First, and most obviously, the multiverse is not directly observable. By definition, other bubble universes are beyond our cosmic horizon. We can't see them, we can't visit them, and we can't perform experiments on them. One intriguing possibility is that our bubble universe might have collided with another bubble at some point in the distant past. Such a collision might leave an imprint on the cosmic microwave background, a kind of scar or anomaly in the otherwise smooth pattern of temperature fluctuations. Physicists Hiranya Paris and Matthew Johnson, along with their collaborators, have searched for such signatures. They've developed models of what bubble collisions would look like and have scanned the CMB data for evidence. So far, they've found nothing definitive. There are some anomalies in the CMB regions that are slightly colder than expected, for instance, but whether these are evidence of bubble collisions or just statistical fluctuations remains unclear. So the multiverse, for now, remains beyond direct empirical confirmation. This troubles some scientists, who worry that we're venturing beyond the realm of testable science into the realm of speculation. Second, eternal inflation and string theory both have their own free parameters. Inflation requires an inflaton field with specific properties. String theory has its own constants, like the number of dimensions and various coupling constants. So even if the multiverse explains why our bubble has the constants it doesn't explain why the multiverse itself has the properties that make eternal inflation and the string landscape possible. You've traded one fine-tuning problem for another. Maybe that's progress. Maybe the multiverse generating mechanism has fewer arbitrary parameters than the laws of physics in any individual universe. But it's not a complete answer. At some level, you still have to accept some things as brute facts. Third, there's a thorny problem called the measure problem. In an infinite multiverse, everything that can happen does happen, infinitely many times. So how do you calculate probabilities? If there are infinitely many bubbles with our physical constants and infinitely many with different constants, How do you say one outcome is more probable than another? Physicists have proposed various ways to address this problem, but there's no consensus. It's a deep conceptual issue that goes to the heart of how we think about probability and prediction in cosmology. Finally, the multiverse has been challenged on more fundamental grounds. In 2018, shortly before his death, Stephen Hawking published a paper with Thomas Hertog that proposed a different approach to eternal inflation. They argued that the traditional picture of eternal inflation, an infinite fractal tree of bubble universes, was based on a flawed application of quantum mechanics. Their approach predicted a finite, more structured multiverse, one that might be amenable to observational tests. Other physicists have questioned whether eternal inflation actually occurs in realistic models. The theory is still being refined, and it's possible that future work will show that the multiverse is smaller, more constrained, or even non-existent. Despite these challenges, the multiverse remains the leading naturalistic explanation for cosmic fine-tuning. It's the idea that most physicists working on fundamental theory take seriously, even if they harbor doubts about specific details. But it's not the only alternative. Other explanations have been proposed, some more speculative, some more conservative. Before we evaluate the philosophical implications of fine-tuning and the Anthropic Principle, let's survey some of these alternative ideas. The multiverse is compelling, but it's not the only game in town. Let's explore some other ways physicists and philosophers have tried to make sense of fine-tuning. One response is to question whether the fine-tuning is as severe as it seems. Maybe life is more robust, more adaptable than we think. Maybe there are forms of chemistry or complexity that we haven't imagined, forms that could exist under very different physical conditions. This argument often gets labeled carbon chauvinism. We assume life has to be carbon-based, has to use water as a solvent, has to resemble the biochemistry we see on Earth. But is that necessarily true? Could silicon-based life exist? Could there be organisms that thrive in cold, liquid, methane, or hot ammonia seas, or even in the plasma of stellar atmospheres? It's a fair question, but it has its limits. While we can imagine exotic forms of life, we're constrained by chemistry and physics. Silicon, for instance, doesn't form the complex, stable chains that carbon does. Silicon bonds are weaker, and silanes, silicon-hydrogen compounds, react violently with water. It's hard to build complex, self-replicating structures out of silicon. Moreover, even if we grant that life could take many forms, the fine-tuning problem doesn't go away. Change the fundamental constants significantly, and you don't just rule out carbon-based life, you rule out chemistry entirely. You rule out atoms. You rule out stars. You get a universe that's a thin soup of particles, or a rapid collapse, or an explosion into nothingness. None of these scenarios seem conducive to any form of complexity, let alone life. So while the carbon chauvinism critique is worth keeping in mind, it doesn't resolve the core puzzle of fine-tuning. Another approach is to hope that a deeper theory will explain the constants. This was Einstein's dream. He hoped that a truly fundamental theory of physics would determine all the constants, that they would emerge from first principles, rather than being arbitrary parameters plugged into equations. In an ideal world, the theory of everything would have no free parameters. You'd write down the equations, solve them, and out would come the masses of particles, the strengths of forces, the value of the cosmological constant, all determined by mathematical necessity. String theory was supposed to be that theory, and in its early days, string theorists hoped it would be unique, that there would be only one way to formulate a consistent theory of quantum gravity with strings. That uniqueness would, in principle, determine everything else. But as string theory developed, the opposite happened. Instead of a unique theory, physicists found the string landscape, with its 500 possible vacua, each corresponding to a different low-energy physics. Instead of solving the problem of free parameters, String theory seemed to multiply it. That said, the search for a deeper theory isn't over. Maybe there's a principle we haven't discovered yet that picks out a particular vacuum in the string landscape. Maybe there's a mathematical structure that explains why certain constants take the values they do. Maybe the theory of everything is out there, waiting to be found. But after decades of effort, we're not there yet. And many physicists are skeptical that we'll ever reach a point where all constants are derived from pure theory with no inputs. There may always be some level at which we simply have to say, this is how things are. A more speculative alternative is Lee Smolin's idea of cosmological natural selection. Smolin, a theoretical physicist, proposed in the 1990 seconds that universes might reproduce through black holes. According to his model, when a black hole forms, it spawns a new universe on the other side of the singularity. That new universe is similar to its parent, but with slightly modified physical constants, like mutations in biological evolution. If this is true, then universes that produce many black holes will have many offspring, and their properties will tend to dominate the population of universes over time. It's natural selection on a cosmic scale. Smolin argued that this could explain fine-tuning. Our universe is good at making black holes, which requires stars, which requires the right balance of forces and constants. So we might expect to find ourselves in a universe optimized for black hole production. It's an intriguing idea, and unlike some multiverse proposals, it makes testable predictions. Smolin suggested that if his theory is correct, tweaking the constants in ways that would increase black hole production should still yield habitable universes. Conversely, tweaking them to decrease black hole production should make habitability less likely. But the predictions haven't held up well. Calculations suggest that you can change some constants in ways that would increase black hole production while making the universe inhospitable to life, and vice versa. So cosmological natural selection doesn't seem to provide the tight link between life-permitting constants and black hole production that Smolin hoped for. Still, the idea has its adherents, and it remains an interesting speculative framework. Then there's the simulation hypothesis, popularized by the philosopher Nick Bostrom. If so, the fine-tuning of the constants could simply reflect the choices of the simulators. They set the parameters to values that allow for interesting, complex phenomena, including simulated observers. This idea has a certain appeal, especially to those familiar with video games and virtual worlds. And Bostrom has argued, somewhat provocatively, that at least one of the following must be true. Advanced civilizations go extinct before developing simulation technology. Advanced civilizations choose not to create simulations, or we are almost certainly living in a simulation. But the simulation hypothesis doesn't really solve the fine-tuning problem. It just pushes it back a level. If we're in a simulation, who created the simulators? What fine-tuning was required for their universe to permit intelligent life capable of building simulations? You end up with an infinite regress. Or you have to accept that at some level, there's a universe with fine-tuning that hasn't been explained. Moreover, the simulation hypothesis is fundamentally untestable. You can't prove you're not in a simulation, just as you can't prove that the universe wasn't created 5 minutes ago with all your memories intact. It's a philosophical thought experiment, not a scientific theory. Each of these alternatives has its merits and its problems. None of them has achieved the consensus that the multiverse has, at least within the physics community. But they remind us that the fine-tuning puzzle remains open, that there are multiple ways to think about it, and that we should be humble about claiming definitive answers. Which brings us to the criticisms. Not just criticisms of specific explanations, but criticisms of the whole fine-tuning enterprise, of the Anthropic Principle itself, of the idea that any of this requires explanation at all. Let's turn now to the skeptics, to those who argue that the Anthropic Principle is, at best, a distraction, and at worst, a surrender of the scientific quest for understanding. Not everyone is impressed by the anthropic principle. In fact, some of the sharpest minds in physics and philosophy have argued that it's confused, trivial, or even dangerous to science. Let's start with the most common objection. The weak anthropic principle is a tautology. A tautology is a statement that's true by definition, that contains no empirical content. All bachelors are unmarried is a tautology. It's true, but it doesn't tell us anything new about the world. It's just unpacking the meaning of the word bachelor. Critics argue that the weak anthropic principle is the same kind of empty statement. We observe conditions compatible with our existence. It's just saying, we exist where we can exist. It's a truism. Of course, we don't find ourselves in conditions that would prevent our existence. How could it be otherwise? The philosophers John Earman, Ernan McMullen, and Jesus Mostarin have been particularly harsh. They write that, in its weak version, the anthropic principle is a mere tautology, which does not allow us to explain anything or to predict anything that we did not already know. If the weak anthropic principle is truly tautological, then it's scientifically useless. Science is supposed to make testable predictions, to explain phenomena, to advance our understanding. A tautology does none of these things. Defenders of the weak anthropic principle respond that even tautologies can be useful if they prevent errors in reasoning. And there are cases in the history of cosmology where failing to account for observer selection effects led scientists astray. Take the Dirac-Dicke debate. Paul Dirac, one of the founders of quantum mechanics, noticed those large number coincidences we mentioned earlier and proposed that they pointed to a deep truth about physics. The gravitational constant must be changing over time. As the universe ages, gravity gets weaker. That would explain why the current age of the universe, expressed in certain dimensionless units, happens to be similar to other large numbers in physics. Robert Dicke, invoking what we now call the weak anthropic principle, showed that Dirac's hypothesis was unnecessary. The coincidence wasn't mysterious at all. It was a consequence of the fact that we can only observe the universe at an epoch when life is possible, and that epoch is constrained by stellar lifetimes, which depend on gravity. The apparent coincidence arises from the requirements of observer existence, not from varying physical constants. So the weak anthropic principle, even if tautological, helped correct a misguided line of theoretical speculation. But critics remain unconvinced. They argue that you don't need a grand principle to avoid Dirac's error. You just need to think carefully about selection effects, something scientists do all the time in other contexts. Giving it a special name and elevating it to a principle makes it seem more profound than it is. There's also a more subtle problem, articulated by the philosopher Nick Bostrom in his work on observation selection effects. The issue is that, even if we accept that we must find ourselves in life-permitting conditions, that doesn't tell us what to expect about the specific values of constants or the structure of the universe. Bostrom calls this the freak observer problem. Imagine a cosmological theory that predicts an infinite universe filled mostly with random noise, but with occasional, incredibly rare pockets where, by sheer chance, conditions happen to be right for observers. According to the weak anthropic principle, we shouldn't be surprised to find ourselves in one of those rare pockets. But should we really believe such a theory? Most physicists would say no. A theory that makes us incredibly unlikely, even if we're possible, seems less attractive than a theory that makes observers relatively common. But how do we formalize that intuition? How do we calculate probabilities when we're reasoning about our own place in the cosmos? Bostrom proposes something called the self-sampling assumption. You should reason as if you're a random observer drawn from the set of all observers. This gives you a framework for updating your beliefs based on anthropic considerations. But it's not without its own problems and paradoxes, and the measure problem in eternal inflation is a particularly thorny example. In short, even if we grant that the weak anthropic principle is useful, figuring out how to apply it rigorously is far from straightforward. Now let's turn to the strong anthropic principle, which faces even harsher criticism. Roger Penrose, the mathematical physicist, has said that the strong anthropic principle tends to be invoked by theorists whenever they do not have a good enough theory to explain the observed facts. In other words, it's a cop-out, an excuse for not doing the hard work of finding real physical explanations. The strong anthropic principle, recall, says the universe must have properties that allow observers. That must implies some kind of necessity, perhaps even purpose or design. And that, critics argue, is where it crosses the line from science into metaphysics or theology. Science, since the Enlightenment, has been about finding causal mechanisms, physical laws that explain why things happen. The strong anthropic principle seems to reverse cause and effect. Instead of physical laws explaining the universe, the existence of observers explains the physical laws. That's teleology explaining things by their purpose or end goal, and modern science explicitly rejects teleological explanations. Moreover, the strong anthropic principle is unfalsifiable. You'd need to observe universes that don't permit observers and show that they don't exist, but that's logically impossible. If no observers can exist in those universes, no one can observe their non-existence. So, the strong anthropic principle, critics say, isn't a scientific hypothesis at all. It's a philosophical or religious belief dressed up in scientific language. Jesus Mosterin has also pointed out a logical flaw in one common argument for the strong anthropic principle. The argument goes, if there are infinitely many universes with all possible combinations of constants, then our kind of universe must exist somewhere. Therefore, the anthropic principle explains fine-tuning. Mosterin counters that this reasoning is fallacious. Just because there's an infinity of something doesn't mean every possibility is realized. There are infinitely many integers, but that doesn't mean every number is an integer. The assumption that an infinite multiverse contains all possible universes is unwarranted, and even if it did contain all possibilities, that still wouldn't explain why this particular universe exists or why we're in it. You'd still face the problem of probabilities and measures. The multiverse itself has come under fierce attack from some quarters. Peter Woit, a physicist and mathematician, has argued that the multiverse makes physics untestable and therefore unscientific. If every possible set of constants exists somewhere, then the theory can't be falsified. Any observation is compatible with the multiverse because any observation exists somewhere in the multiverse. Paul Steinhardt, one of the founders of inflation theory, has become a vocal critic of eternal inflation and the multiverse. He argues that the theory has become so flexible, with so many free parameters, that it can accommodate any observational result. That means it doesn't actually predict anything, and therefore, by Karl Popper's criterion of falsifiability, it's not science. Defenders of the multiverse respond that it's a prediction of well-established theories, inflation, and string theory, not an ad hoc hypothesis invented to explain fine-tuning. If those theories are correct, the multiverse follows. We can't just ignore it because it's inconvenient or philosophically unsettling. But even among multiverse proponents, there's acknowledgement that the situation is uncomfortable. We're in a strange position where our best theories seem to predict things we can never observe. That challenges our traditional notions of what science is and what it can achieve. There's also the inverse gambler's fallacy objection. Imagine you walk into a casino and see someone roll double sixes. Do you conclude that this person has been rolling dice for a long time because double sixes are unlikely and therefore must have taken many attempts? Most people would say no, you're seeing one roll, and double sixes can happen on the first try. Now apply this to the multiverse. We see one finely tuned universe, Does that give us reason to believe in many universes? Critics say it's the same fallacy as the casino example. The fact that our universe is unlikely doesn't, by itself, provide evidence that many universes exist. Defenders respond that the analogy breaks down because we're not external observers. We're inside the system. We're conditional on the existence of observers, and that changes the probability calculus. It's more like asking, given that someone observed double sixes, how likely is it that there were many dice rolls? And in that case, many rolls does become more probable. The debate over these arguments is technical and ongoing. There's no consensus, even among experts, about whether the multiverse is a legitimate scientific hypothesis or a sign that physics has lost its way. What's clear is that the anthropic principle and fine-tuning raise profound questions about the nature of scientific explanation. Can we ever explain why the fundamental constants have the values they do? Or are some things simply brute facts, givens that we have to accept? Can a theory that invokes unobservable entities, like other universes, still be scientific? What role, if any, should considerations of observers and life play in fundamental physics? These aren't just technical questions. They're philosophical questions about what science is, what it can achieve, and what kinds of answers count as satisfying. They're questions about the boundary between science and metaphysics, and whether that boundary is sharp or blurry. And they're questions that don't just matter to physicists and philosophers. They matter to anyone who wonders about their place in the cosmos, about why the universe is the way it is, about whether existence has meaning or purpose. Let's turn now to those larger questions. To what the anthropic principle might mean for us as humans, as conscious beings, reflecting on a universe that permits our existence. For 5 centuries, the trajectory of astronomy and cosmology has been one of progressive demotion. Copernicus showed that Earth is not the center of the solar system. Later astronomers showed that the solar system is not the center of the galaxy. Edwin Hubble showed that our galaxy is just one among billions, scattered through a vast and expanding universe. Every step has taken us further from the center, made us smaller and less special. The Copernican principle, the idea that we occupy no privileged position in the cosmos, has become a guiding philosophy. We are not special. We are not central. We are, cosmically speaking, insignificant. But the anthropic principle complicates this narrative. If the universe is finely tuned for life, if the constants fall within narrow ranges that permit complexity in observers, then maybe we're not as insignificant as we thought. Not in the sense that we're physically central, we're not, but in the sense that our existence places constraints on what kind of universe we can inhabit. If fine-tuning is real, it suggests that observers, anywhere, are rare. The parameter space that allows for life is a tiny fraction of all possibilities. Most conceivable universes are sterile, empty, lifeless. Universes like ours, where stars shine and atoms bond and consciousness emerges, are extraordinary outliers. So which is it? Are we insignificant specks on an ordinary planet? Or are we remarkably fortunate to exist at all? The anthropic principle forces us to hold both truths in tension. We are not the center, but we are not typical either. We are peripheral in space, but central in a different sense, central to the question of why the universe has the properties it does. This has implications for how we think about life beyond Earth. If fine-tuning is severe, and if our universe is the only one, then life might be extraordinarily rare. We might be alone, or nearly so, in a cosmos that is mostly hostile to our existence. On the other hand, if the multiverse is real, then there are countless universes, and in some fraction of them, the constants permit life. Within our universe, the conditions might be common enough that life has arisen in many places. We might have company. The search for extraterrestrial intelligence, SETI, has been going on for decades, with no confirmed detections. Some see this as evidence for the rare Earth hypothesis. That while microbial life might be common, complex intelligent life is vanishingly rare, the result of an improbable chain of events that may not have occurred anywhere else in our galaxy. The Anthropic Principle doesn't settle this debate, but it shifts how we frame it. We ask, given that we exist, what can we infer about the frequency of life? And that's a subtly different question, one that requires careful thinking about selection effects and probabilities. There's also the question of purpose and meaning. The traditional religious perspective holds that the universe was created for a reason, that human life has a purpose, that there's a cosmic plan. The materialist perspective holds that the universe is a brute fact, that life arose by chance, that there's no inherent purpose or meaning. Where does the Anthropic Principle fit into this dichotomy? Some religious thinkers have embraced fine-tuning as evidence for God. If the constants are finely tuned, the argument goes, there must be a tuner. The precision required to get a life-permitting universe suggests design, intention, a creator who wanted life to exist. This is a modern version of the argument from design, updated with cosmology and particle physics instead of the complexity of living organisms. And it's a powerful argument, at least rhetorically. The idea that all this precision is just luck seems to strain credulity. But the multiverse offers a counter-narrative. If there are countless universes with different constants, then the fine-tuning we observe is simply a selection effect. No designer needed. We exist in a life-permitting universe for the same reason fish exist in water, because that's the only place they can be. The multiverse, in this view, removes the need for God, except, of course, the multiverse itself raises new questions. Why does the multiverse exist? Why does it have the properties that allow eternal inflation and the string landscape? Why does it generate bubble universes at all? You can push the mystery back, but you can't eliminate it entirely. Some theologians have responded by arguing that God could work through a multiverse, that a divine creator might choose to bring into being a reality that includes countless universes. The multiverse doesn't disprove God, it just changes the nature of the question. These debates are unlikely to be resolved by physics alone. Science can tell us about the structure of reality, the values of constants, the evidence for or against a multiverse, but it can't answer the question of why there's something rather than nothing, or whether that something has meaning or purpose. Those are questions at the boundary of science and philosophy, and they may not have objective answers. What we can say is this: the Anthropic Principle highlights the strange and remarkable fact that the universe permits us to ask these questions. We are matter that has become conscious of itself, carbon and oxygen and hydrogen arranged in such a way that we can contemplate the cosmos and our place in it. That's extraordinary. Regardless of whether it's the result of design, chance, or necessity, we are question-asking creatures in a universe that didn't have to allow questions to be asked. And that paradox, that strangeness, is perhaps the deepest lesson of the Anthropic Principle. We don't know why the constants take the values they do, but we know we're here, and we know that fact is, in some hard-to-define sense, cosmically improbable. Maybe that's enough. Maybe the point isn't to resolve the mystery, but to appreciate it, to live with the awareness that our existence sits at the intersection of physics and philosophy. Let's take stock. What do we actually know, and what remains uncertain? We know the universe appears finely tuned. Multiple fundamental constants fall within narrow ranges that permit atoms, stars, chemistry, and life. This isn't speculation, it's the result of well-tested physical theories. Change the gravitational constant, the strong force, the cosmological constant, or other parameters by small amounts, and the universe becomes inhospitable to complexity. We know the weak Anthropic Principle is logically sound, even if it's sometimes dismissed as trivial. We do observe conditions compatible with our existence, and failing to account for that selection effect can lead to errors. We know that cosmic inflation is supported by observational evidence. The patterns in the cosmic microwave background match the predictions of inflationary theory with remarkable precision. We know that string theory, if correct, predicts a vast landscape of possible vacua, each corresponding to different low-energy physics. But we also know that string theory remains unverified. No experiment has detected strings, extra dimensions, or any of the distinctive signatures that would confirm the theory. We don't know if other universes exist. Eternal inflation predicts them, but we can't observe them directly. Searches for indirect evidence, like bubble collision signatures in the CMB, have so far come up empty. We don't know if the fine-tuning requires explanation at all. Maybe there's a mathematical principle we haven't discovered that determines everything, or maybe some things are just brute facts, and we have to accept them. We don't know how to solve the measure problem in eternal inflation. How do we calculate probabilities in an infinite multiverse? Different proposals give different answers, and there's no consensus. We don't know if the strong anthropic principle means anything substantive. Does the universe must permit life in any meaningful sense? Or is that just a suggestive way of restating the weak principle? Current research continues on all these fronts. Astronomers are analyzing data from the James Webb Space Telescope, which can peer further back in cosmic time and might reveal new clues about the early universe. Physicists are working on quantum gravity theories that might replace or refine string theory. Cosmologists are developing more sophisticated models of inflation and searching for testable predictions. There's also ongoing work on the foundations of quantum mechanics, particularly in connection with John Wheeler's ideas about observers and the participatory universe. Wheeler speculated that observation plays a fundamental role in bringing reality into being. These ideas remain on the fringe of mainstream physics. The next decade could bring significant developments. Better measurements of the CMB, gravitational wave detections, and advances in particle physics might all shed light on the big questions, or they might deepen the mystery, revealing new layers of complexity we haven't anticipated. What's certain is that the anthropic principle isn't going away. Whether you see it as a profound insight or a pseudo-explanation, it's become part of the conversation about cosmology and fundamental physics. It forces us to think about our place in the universe, about the relationship between observers and the observed. And it reminds us that science, for all its rigor and precision, still operates at the boundary of the known and the unknown, the empirical and the philosophical, the factual and the meaningful. So here we are, back where we started. You exist. You are reading or hearing these words, processing information, forming thoughts. Neurons fire in patterns shaped by evolution, by development, by experience, and all of that is possible because of a long chain of cosmic events, stretching back to the first fraction of a second after the Big Bang. If gravity had been slightly stronger, the universe would have collapsed before stars could form. If the strong nuclear force were different, carbon wouldn't exist. If the cosmological constant were larger, space would have expanded too quickly for galaxies to coalesce. Change any of these, and you're not here. Change any of these, and there's no complexity, no chemistry, no consciousness. Just a vast, empty, structureless cosmos, devoid of anything that could ask questions or ponder mysteries. But the constants are what they are, and so you're here, a brief arrangement of atoms, momentarily aware of its own existence. The anthropic principle tries to make sense of this. It says, don't be surprised by fine-tuning, because you could only exist in a finely tuned universe. If the multiverse is real, then it's a selection effect. You're in one of the rare bubbles where the constants permit life. If the multiverse isn't real, then maybe it's design, or necessity, or luck, or something we haven't imagined. But whatever the explanation, the fact remains. You are here. The universe permits you. It allows complexity, structure, stars, planets, life, thought. It allows creatures made of stardust to contemplate their own origins, to puzzle over the fine-tuning that made them possible. To ask why, perhaps that's the deepest mystery. Not just that the universe is finely tuned, but that it's produced beings capable of noticing the fine-tuning. We are the universe looking at itself, asking questions about itself, marveling at its own improbability. The Anthropic Principle doesn't answer the ultimate question. It doesn't tell us why there's something rather than nothing, why the laws of physics take the form they do, whether existence has a purpose. But it sharpens those questions. It makes us aware of the peculiarity of our situation, the improbability of our existence, the strangeness of being observers in an observed universe. And maybe that awareness, that sense of wonder, is itself a kind of answer. Not a final answer, not a complete answer, but an answer that says, you are part of something vast and mysterious, something that didn't have to be, but is, something that permits questions, even if it doesn't provide ultimate answers. Science will continue. Physicists will keep searching for deeper theories. Astronomers will keep probing the cosmos for clues. Philosophers will keep debating what it all means. And maybe, eventually, we'll understand why the universe has the properties it does. Or maybe we won't. Maybe some mysteries are too deep, some questions too fundamental. Maybe we'll always be left with irreducible facts, givens that we can describe but never fully explain. Either way, we're here. You're here. And the fact that you can pause right now and contemplate your own existence, the improbability of your presence in this vast cosmos, that fact is as remarkable as anything in physics. So rest now, drift gently toward sleep, knowing that you are part of a universe that, against all odds, permits you to exist. A universe where matter has become conscious, where consciousness can ponder its own origins, where questions can be asked even if answers remain elusive. The Anthropic Principle reminds us that we're not just passive observers, recording data about an indifferent reality. We're participants in the cosmic story, products of it and questioners of it, both inside the universe and able to step back and marvel at it. And in that paradox that we are simultaneously insignificant specks and central questioners, we find something profound. Not certainty, not final answers, but a sense of wonder that connects us to the deepest mysteries of existence. If this exploration of fine-tuning, multiverses, and cosmic mystery has resonated with you, if it's given you something to ponder as you drift towards sleep, or simply made the universe seem a little stranger and more wonderful, consider leaving a like. It helps others discover these journeys through science and philosophy. And if you'd like more deep dives into the questions that live at the edge of knowledge, where physics meets meaning and observation meets wonder, subscribe. Your support makes these long-form investigations possible. These attempts to make sense of a cosmos that permits us to question it. Rest now in the peace that comes from contemplating vastness. The universe that allows you to exist also allows you to wonder. And that wonder, perhaps, is as improbable and precious as anything else we've discussed tonight. You are here, aware, questioning. And that simple fact that reality permits observers to observe it is the Anthropic Principle's final gift. Not an answer, but an invitation to marvel at the strangeness of existence itself. Good night, fellow travelers in this improbable universe. May you rest well, knowing you are part of something both comprehensible and ultimately mysterious, both understood and forever strange.